Let's go back and review the end of chapter 3 a little bit before we go on to optimization problems today. I want to focus on something we've already talked about first, the increasing function theorem, and not only try to make sure we understand what the increasing function theorem says, but also what it does not say that you could easily think it says if you're not thinking carefully about it. So we've got some assumptions, some hypotheses here. We've got a function f. It's continuous on the closed interval from a to b, differentiable on the open interval from a to b. The inequalities, closed interval, we include the endpoints. The strict inequalities there means do not include the endpoints. Could it be continuous and differentiable on a bigger interval? Yes, it could be continuous and differentiable on the entire real number line. But for the purposes of this theorem, we're just focused on one particular interval. 2 bullet points, meaning 2 parts of the theorem here. If f prime is always positive over the entire open interval, then you can conclude that f is increasing on the closed interval. And that really is true. The endpoints effectively don't matter. The second bullet says if f prime of x is greater than or equal to 0, non-negative is the best way to say that. Don't say positive there because technically 0 is not positive. Being greater than or equal to 0 means it's not negative. On the open interval, then f is non-decreasing on the closed interval. What does non-decreasing mean? Well, it means it's either increasing or maybe constant. But it's not going down. It's not decreasing. Okay? You think about this theorem with the picture, it makes some pretty good sense. If we know the derivative is positive on the open interval for a nice continuous differentiable function, the function's got to be going up. Are there examples of functions that are continuous on the closed interval but not and differentiable on the open interval but not at the endpoints? Yeah, there are. What typically happens in such situations is that they have vertical tangents at the endpoints. Maybe something like this. That would be an example of a graph, at least. I didn't write a formula, but a graph at least that is continuous in the closed interval, differentiable in the open interval, not including the endpoints, and is in fact not differentiable at the endpoints. I'm trying to draw it in such a way that the tangent lines at these endpoints effectively are vertical. The slope goes to infinity. That would be a way it could fail to be differentiable at the endpoints. But it does satisfy the hypotheses of the theorem. If the derivative is always positive on the open interval, the function's increasing. And yeah, you can see it with the graph. But we saw earlier this week or last week that you need to use the mean value theorem to prove this. It's much harder to prove than you would imagine. Okay, but a graph makes it seem reasonable. However, just because something seems reasonable doesn't mean it's true. This is the first real subtle point I want to make, to not misunderstand what this is saying. Suppose I have the same background hypotheses here. Suppose I've got a function f that's continuous on the closed interval and differentiable on the open interval, but I switch around the parts that come after the word if and the part that comes after the word then. I'll go ahead and write an if-then statement, switching those around. If f is increasing on the closed interval, then f prime of x is positive on the open interval. This is not the increasing function theorem. It's got this, I'm assuming again, it's got the same background hypotheses, continuous on the closed interval, differentiable on the open interval. But for this first bullet, the part that comes after the f prime of x being positive on the open interval, and the part that comes after the then, the f increasing on the closed interval, I switched them around. That's a different if-then statement. And guess what? Even though it seems reasonable, f is increasing, therefore the derivative must be positive. That's actually false. This is false. meaning it's not a theorem. And you sit here and you wonder, well, how could it be false? If the graph's going up and it's a nice function, how can't the derivative always be positive? It sounds true, and you might even say it's usually true for most examples, but I can come up with an example that demonstrates it's false, and it's a fairly simple example. Examples that demonstrate that statements are false are called counterexamples. Counterexample. Okay, I'm going to write it down. It's fairly simple. You might look at it and say, well, oh, that's such a silly counterexample, but it actually is fundamental to realize it is a counterexample. If f of x equals x cubed, and my interval from a to b, I'll use interval notation. O, for example, goes from -1 to 1. That is a function that's increasing, strictly increasing, in fact, on this interval, but the derivative is not always positive. Really? Yeah, f prime of x is 3x squared. So f prime of 0 is 3 times 0 squared is 0. And 0 is not greater than 0. It's not positive. The graph is always going up, though, over the entire interval from -1 to 1. And in fact, over any interval, any subinterval of that, including any interval near 0, no matter how close it is to 0. This is the graph of f of x equals x cubed. The graph is going up. That doesn't stop it from having a horizontal tangent line at 0. And horizontal lines are not increasing, they're constant. You could say they're non-decreasing, but they're not increasing. Yes, the tangent is horizontal, but the function itself is not. A very subtle but important point to realize. Why is the tangent line horizontal? Well, it's because the derivative is 0. But why, intuitively, the closer you zoom in on the green graph near the origin, the more and more horizontal the graph will look. We can try it with the calculator. As long as you zoom in the x and y direction at the same rate with the same scale. X cubed is my function. I'll pick an initial window going from -1 to 1 in both directions. Graph it. There it is. Now I'm going to zoom in near the origin. Make the scales the same in both directions. What I mean is, now I'll, for example, go 10 times closer in both the x and y directions. -0.1 to +0.1 for x, and also -0.1 to +0.1 for y. Graph it. Ready? I'm about to graph it. Watch it. I don't even see it. Where's the graph? Well, it was graphed. You just can't see it. It looks indistinguishable from the x-axis. That's why we don't see it. It's so close to being horizontal at the origin that the tangent line is horizontal, but the graph itself is actually not horizontal. You plug in any number that's not 0, but close to 0 into x cubed, you will get still a number that's non-zero. It'll be a lot closer to 0. Again, that's 10,000 times closer to 0 than 0.01 is, but it's still not equal to 0. Here's something even more subtle. You ready for this? Going back again to the increasing function theorem, if f prime is always positive on an open interval, then f is increasing on the closed interval. You might think that because of this, if f prime is positive at one point, then f must be increasing on some interval near that point. Say that again. You might think if the derivative f prime is positive, say at 0, f prime of 0 is positive, that f should be increasing on some interval near 0. Maybe a very small interval, but it should be increasing, right? If the tangent line has got a positive slope. That is actually false. Coming up with an example of that is much harder, though. I will show you an example, but I wouldn't expect you to think of an example like this on your own. If f of x, oh, this has got to be a piecewise function, actually, is x squared times sine of 1 over x, o plus x, if x is not 0, and 0 if x equals 0, I claim that f prime of 0 is positive. In fact, I claim f prime of 0 is 1, I claim. I'm not going to prove this, but I claim that's true. But f is not increasing, not strictly increasing on any interval containing 0. In fact, even more than this, I claim this is a nice function. It's continuous and differentiable everywhere. I think we've seen something like this before. I got the sine of 1 over x. Do you remember what happened with that function back in chapter 1 and 2? There was the squeeze theorem, limits, and there were infinitely many oscillations. I'm multiplying that by x squared, so the oscillations are getting squeezed down to being very small oscillations as x goes to 0. Then I'm adding x to make the slope positive. Let's see what the graph looks like here, if our calculator can give us a decent graph of it. X squared times sine of 1 over x plus x. Let's pick a window further away from 0 at first. How about -5 to 5 and just see what it looks like on this scale? Okay, doesn't look that interesting, actually. Looks almost like a straight line with maybe a little bit of a wiggle in there. Let's go in closer. -1 to 1. Yeah, the wiggle is getting a little bit more pronounced. -0.1 to +0.1. Yeah, we see some definite wiggles there. But it seems like it's getting straighter near that point, doesn't it? The wiggles are bigger the further you are away from the origin there. I'm actually not positive how it's going to display this as I continue to go in closer. Let's see. It looks straighter, actually. It looks like nothing weird's happening, but looks are deceiving. It does look a little weird near the edges. The oscillations are getting a little bit bigger. Looks are deceiving there. It's actually oscillating infinitely often. It has to be, because I got sine of 1 over x over in there, and 1 over x as x goes to 0 goes to infinity. So I got sine of something going to infinity. It's got to go through infinitely many oscillations in this part of the function, at least. If I zoomed in near any one of these things that's slightly away from 0, maybe I should try doing that. Maybe I should go from, how about, what should I pick here? 0 to positive. Well, let's keep the 0.01 there. I'm not quite so sure how this is going to look. We probably won't see it. I'd have to do a lot of experimentation to try to get it right. You can kind of see it. It's a little bit jagged in here. Maybe more jagged than a typical straight line would look on a calculator. There are actually infinitely many oscillations that all go both up and down. But they're just getting so small as you get near the origin that you can't see them anymore. And in fact, it is differentiable at 0, and the derivative at 0 is 1. It does look more and more like a straight line with a slope of 1. becomes indistinguishable, but that's just because you're not looking carefully enough. There's a really infinitely many oscillations still. Oh, that's weird. Do you have to know this for the test? No. But I'm just letting you know, really weird things can happen. Unexpected things can happen when you're talking about functions and their derivatives. Things that seem like they should be true, but they're not. The increasing function theorem is a theorem. It is definitely true. But you look at the converse, it can be false. You look at f prime being positive at just one point, that's not good enough to guarantee f itself is strictly increasing. Actually, this works a little bit better in Mathematica. I think what we can do in Mathematica pretty quickly is we can see both the graph of the function itself and its derivative. And that'll be a helpful thing. I can define a piecewise function in Mathematica, by the way. I can do this button and do x squared times sine of 1 over x plus x if x is not 0, and 0 otherwise if x is 0. I can plot not only the function itself, but the derivative near 0. And let's make the graph of the original function blue and the graph of its derivative red. What will we see? Oh, craziness in the derivative. The derivative, f prime of x, whose formula is that when x is non-zero, has infinitely many oscillations that don't decrease in amplitude. And if you look real close to the origin here in the vertical direction, the red graph's values always do go negative slightly. You can see it definitely over here and over here. It looks like maybe it's not happening in here, but that's a little bit deceiving. It's just because the graph's not plotting enough points. If I plot more points, it'll be a little smoother. Yeah, I still can't tell. Let me zoom in even closer. Oops, not that. Yeah, the red graph is continuing to go negative as I get closer and closer to 0, meaning the blue graph does have places where it decreases. I go in even closer. Yeah, I still see that red graph going down below 0 sometimes. This is a little deceiving here. That's computer error. It does continue to go negative. The numbers are getting so small that the computer is making some errors, not doing things perfectly. Okay. So I'm just, again, trying to make you aware that weird things can happen. You should know this example for exam 2, this counterexample. You don't have to know this counterexample for exam 2. I just wanted to show it to you. We also have the constant function theorem in the reading. Suppose f's continuous and differentiable. If the derivative is always 0, then the function's constant. Tangent lines are always horizontal. The graph of the function itself's got to be horizontal. You would think there's nothing to prove there. Like, that's so obvious. But proving it, this is a theorem, it is true. Proving it takes the mean value theorem. And remember I said if you prove the mean value theorem from scratch, it takes an entire semester. What do I mean by from scratch? I mean, like, only assuming you know how to do arithmetic. That's what I mean, like, from scratch. If you have higher level assumptions, as we do in a class called real analysis, then you could prove the mean value theorem in about a month, month and a half. But this requires the mean value theorem to prove it. Astonishing. Such a simple sounding theorem. It is a theorem, though. It is true.